Good morning. Today we are going to deal with the second part of electrical conductance. In the first chapter, we have deal with the introduction of the electrical conductance, and we have deal with the Faraday's laws of electrolysis. So in this part, we are going to deal with the molar conductance and variation of molar conductance on dilution, and we can also discuss the determination of degree of dissociation using Oswald dilution law. Before coming to the molar conductance, we are familiar with the conductance. What do you mean by conductance? Conductance is actually the reciprocal of resistance. So resistance, we are familiar with the resistance. Resistance is the resistance to flow of current, and the inverse or reciprocal of the resistance is called conductance. So the unit of conductance or conductance is expressed as Siemens, ohm inverse, or ohm inverse, or mho. And we are familiar this conductance is directly proportional to the area of cross section and inversely proportional to the length of the wire. So the conductance is equal to a constant into A by L, and where conductance is equal to a constant K into A by L, and where K is called the conductivity, or it is also called a specific conductance. So we can measure this conductivity. The conductance can be generally measured, and the conductivity can be measured using this equation, that is conductance into L by A. So L by A is actually a constant, and that constant is called a cell constant. And the unit of the cell constant is equal to, here we can see that this L can be represented as centimeter and A can be represented as centimeter square. So centimeter get cancelled. So the unit of cell constant is centimeter inverse. So, or meter inverse. So we can represent the unit of cell constant as centimeter inverse or meter inverse. So we have already mentioned that the specific conductance is equal to 1 by rho, or the specific resistivity, that is 1 by rho, that is the specific resistance. And so this specific conductance is equal to conductance into L by A. So L by A is known as the cell constant, and the unit of specific conductance is ohm inverse, centimeter inverse. Then we can move to the molar conductance. So molar conductance is nothing but it is the conductance of all the ions furnished when 1 mole of electrolyte dissolved in VCC of the solution. So molar conductance is represented as K into V, where K is the specific conductance and V is the volume of solution containing 1 gram mole of the electrolyte. The conductance of all the ion furnished by 1 gram mole of electrolyte dissolved in the solution. So it can be represented as the molar conductance is equal to specific conductance into 1000 divided by molarity. So the volume of the solution is equal to 1000 divided by molarity, where K is the specific conductivity. Then variation of specific conductance on dilution. So we can see that the specific conductance is the conductance offered by 1 centimeter cube of the solution, when the area is 1 centimeter square and length is 1 centimeter cube. So specific conductance is the conductance offered by 1 centimeter cube of the solution. So here we can see that since the number of ions per unit volume decreases on dilution. So dilute ചെയ്യുമ്പോൾ എന്ത് സംഭവിക്കും? The number of ions present inside this cube decreases. So number of ions decrease ചെയ്യുക എന്ന് പറഞ്ഞാൽ എന്തായിരിക്കും? Specific conductivity decreases. So specific conductivity is directly proportional to concentration. So as the concentration decreases, specific conductivity decreases. In the case of molar conductivity, here we can see that the specific conductivity decreases on dilution, but we can see that the volume increases on dilution. So on compared to the specific conductance and volume, the volume is very higher, and so the molar conductivity or molar conductance increases on dilution. അപ്പോൾ സ്പെസിഫിക് കണ്ടക്ടൻസ് കുറയാണ്. സ്പെസിഫിക് കണ്ടക്ടൻസ് കുറയുമ്പോൾ നമുക്കറിയാം ഡൈല്യൂട്ട് ചെയ്യുമ്പോൾ എന്ത് ചെയ്യും, വോളിയം കൂടും. സോ വോളിയം കൂടും. അപ്പൊ ഇത് രണ്ടും കൂടെ അതിന്റെ പ്രോഡക്റ്റ് ആണ് നമ്മുടെ മോളാർ കണ്ടക്ടൻസ് വരുന്നത്. സോ ഇത് കുറയുന്നു, സ്പെസിഫിക് കണ്ടക്ടൻസ് കുറയുന്നു, വോളിയം ഇൻക്രീസ് ചെയ്യുന്നു. So that we can see that the molar conductance increases on dilution. So in the case of a strong electrolyte, we can see that in the case of strong electrolytes are fully ionized, and if we increases the dilution or if it decreases the concentration, we can see that the conductance increases, and we can see that it approaches to a particular value when it approaches a zero. And so the molar conductance at infinite dilution or limiting molar conductivity is called the molar conductivity at infinite dilution, or the molar conductance when the concentration tend to zero is called the molar conductivity at infinite dilution. Molar conductivity at infinite dilution. It is represented as lambda 0. അപ്പോൾ മോളാർ കണ്ടക്ടൻസ് എന്താന്ന് പറഞ്ഞു? മോളാർ കണ്ടക്ടിവിറ്റി increases on dilution and it reaches a particular value at the concentration tend to 0, and that value is called the lambda 0, and it is actually the molar conductivity at infinite dilution. But in the case of weak electrolyte is not fully ionized, and so when we decreases the concentration, the degree of dissociation will be increased. So more number of ions will be produced during this dilution process. So what will happen? So at first the conductivity will be very low, and when we increases the dilution or when we decreases the concentration, we can see that there will be a sharp increase in conductance. അപ്പോൾ ഇതിന്റെ അഡ്വാൻറ്റേജ് എന്താന്ന് പറഞ്ഞിട്ടുണ്ടെങ്കിൽ, when we look at this weak electrolyte and strong electrolyte, we can see that we can determine the molar conductivity at infinite dilution by extrapolating the graph. നമ്മൾ സ്ട്രോങ് ഇലക്ട്രോലൈറ്റ് എടുത്തു, ആ സ്ട്രോങ് ഇലക്ട്രോലൈറ്റ് ഇങ്ങനെ പ്ലോട്ട് ചെയ്തിട്ട് എന്ത് ചെയ്യണം, അത് എക്സ്ട്രാപൊലേറ്റ് ചെയ്ത് നമുക്ക് ഇവിടെ കിട്ടുന്ന വാല്യൂ എന്ന് പറയുന്നത് മോളാർ കണ്ടക്ടൻസ് അറ്റ് ഇൻഫിനിറ്റ് ഡൈല്യൂഷൻ. That value can be determined for strong electrolyte. But look at the weak electrolyte. In the case of weak electrolyte, we cannot determine the molar conductivity at infinite dilution. കാരണം നമുക്കറിയാം ഇത് നമ്മൾ പ്ലോട്ട് ചെയ്ത് ഇങ്ങനെ വരുന്നത്, ഇത് പ്ലോട്ട് ചെയ്ത് എന്താ നേരെ ഇങ്ങനെ മുകളിലേക്ക് പോവുകയുള്ളൂ. സോ y ആക്സിസിൽ ടച്ച് ചെയ്യില്ല. So that means we cannot determine the molar conductivity of weak electrolyte by direct method. So we have to use another technique or another method or another law, that is called a Coloratius law. So before coming to the Coloratius law, we can see that this is Oswald dilution law and dissociation constant of weak electrolyte. So consider a weak electrolyte, this AB. On dissociation, we will get A plus and B minus in aqueous solution. So the concentration at the initial stage is C, and the concentration at the final stage is 0. So at equilibrium, we can see that this alpha is the degree of dissociation. So C alpha and C alpha for A and B, and the concentration of the AB will be is equal to C into 1 minus alpha. ഇവിടെ നമ്മുടെ 1 ആണ്, C into 1 ആയിരുന്നു, 1 ന്ന് ആൽഫ degree of dissociation പോയി, so 1 minus alpha. So at equilibrium, the equilibrium can be denoted as A plus into A minus divided by AB, that is concentration of the reactant by concentration of the product. So that is equilibrium constant K is equal to K C alpha into C alpha. This is A യുടെ concentration C alpha ആണ്, B യുടെ concentration C alpha ആണ്. the concentration of AB എന്ന് പറയുന്നത് എന്താണ്? C into 1 minus alpha. That is C alpha square into 1 minus alpha. And so this is actually the Oswald dilution law. But in the case of weak electrolyte, alpha is very, very small. Hence, 1 minus alpha can be represented as alpha. So Ka is equal to എന്താണ്? C alpha square divided by 1. 1 minus alpha, 1 minus alpha യിൽ വരുന്ന 1 minus alpha എന്ന് പറയുന്നതിൽ ആൽഫയുടെ വാല്യൂ that is very, very small. That is 1 minus alpha is equivalent to 1. So Ka is equal to C alpha square, and alpha for weak electrolyte is equal to Ka by root C. So in the case of H plus ions, we can determine the concentration of H plus ion is equal to C into root Ka by C. So this is actually called the Oswald dilution law. So in this section we have discussed with the specific conductance, molar conductance, the variation of specific conductance and molar conductance on dilution, the molar conductance at infinite dilution, and the molar conductance at infinite dilution for strong electrolyte can be very easily determined, but in the case of weak electrolyte we cannot determine. Direct method we cannot determine the molar conductance at infinite dilution. And then we have discussed about the Oswald dilution law, and that can be used for the determination of degree of dissociation of weak electrolyte.